So it might be useful for us to do some practice with antiderivatives. So we have, of course, our warm-up problem. We have the integral of e to the x plus 1 quantity squared dx, and there's 5 candidates listed there. Now, these are all different functions, so they can't all be antiderivatives. So only one of these is the right answer. Which one is it? A, B, C, D, or E? Did anybody work it out?
I want to say A for simplicity's sake, but I haven't.
Ah, I know. A is so tempting, right? So tempting. But maybe it's tempting because it's right. B, huh? Again, very tempting. Maybe it's tempting because it's right. Or maybe it's not. Okay. Did anybody work it out? What? D is the right answer. Okay. 1/2 e to the 2x plus 2e to the x plus x. You're like, what? Okay, so the thing is, there's basically a rule of thumb. You got 8, maybe 10 if you're really good at memorizing things. 8 or 10 things you know how to integrate, which is another way of saying take the antiderivative. If it's not on that list of 8 or 10 things, you have work ahead of you. And so you say, okay, well, what's the work? Because this is not on our list. It's a very short list. So you say, well, I see a square. So you square it. So a squared plus 2ab plus b squared. So, oh, that's like e to the 2x plus 2e to the x plus 1. And now you just integrate term by term. The integral of e to the 2x, e to the 2x, divide by 2. That 2 up in the exponent is why you need to divide by 2 here. It's essentially related to a very simple case of the chain rule. And we'll do more interesting cases of the chain rule soon. It's one of our favorite things about integration. Integral of e to the x is e to the x. Don't forget the constant in front. Integral of 1 is x. And of course, as all antiderivatives should, make sure you include the plus c. Because if you don't, you're going to lose a point. And we don't want to lose a point. We want all the points. Got to get them all. All right. Well, our thought for today. Famous quote, "A ship in harbor is safe, but that is not what ships are built for." And this is basically a reminder. It's important to get out of your comfort zone because we're trying to make you amazing. Well, you already are amazing. We're trying to make you amazinger. I don't know if that's a real word, but let's pretend it is. And but as you pick up these skills, you need to get outside of your comfort zone, expand your boundaries, be bold, and try things. And so that's the thought for today. All right. Well, as I said, we should do some practice with antiderivatives. Let's see, what's a good one to start with? Maybe we'll start with this one. This one seems the most harmless. Okay. Find the antiderivative, or the integral of y minus 3 times the square root of y plus y to the minus 1 plus 7y over y squared dy. All right. Now, maybe we're lucky. Is that one of the 8 integrals that we know how to do? No. Yeah. The 8 that we know, it's a very short list. Okay, so if it's not one of the 8, then we start saying, what can we do? So what can we do here?
Split it up.
Well, split it up. I mean, ultimately the goal is to think about ways to rewrite. What are things we can do to help us rewrite?
We can bring the 2 up. And the 1.
So here you should be thinking algebra, algebra, right? Because algebra, that's like our go-to thing. What's algebraic things we can be doing here? Like you have multiplication. What can you do? All right. People are stumped about this. So here, we'll try to jog your memory. You're multiplying things together. What can you do? Foil. Great. You got it on the first try. Nice. You're good at this game. Okay, so we can foil. All right. Now, the other thing, of course, square root of y to the half. So, first, y times y to the 1/2, also known as y to the 3/2. Outer, y times y to the -1 will become just simply 1, y to the 0. 3 times y to the 1/2, 3y to the 1/2. And 3 times y to the -1, 3y minus 1, plus 7y. That's just on the end. That's not part of your FOIL. Over y squared. Now what can you do? Yeah, we can split it up. Because we've got that, we mentioned this before. These are the good plus and minus signs. So we can say, hey, we can break things up. Breaking up is easy to do. In this case, y to the 3/2 divided by y squared. What would that be? Y to what power? What do you do with the exponents? Subtract 3/2 minus 2, -1/2. 1 divided by y squared, how will we write that? Y to the -2. Y to the 1/2 divided by y squared, how will we write that? Y to the -3/2. Y to the -1 divided by y squared becomes y to the -3 minus 1 subtract 2. Y divided by y squared will become 1 over y. You're like, what? Why did you do that? You're breaking your rule. Because there's a special item on our list. Very special. Y to the -1 behaves differently, so we treat it differently. 1 over y. Okay. And now, again, we break up over addition and subtraction. So this is antiderivatives, or if you like, integrals are linear. So we do it term by term. So the rule, add 1 to the exponent. So here, -1/2 plus 1 becomes +1/2. And then what do? You take your exponent and divide in front. How do you divide by 1/2? Times by 2. Okay, add 1 to the exponent. Y to the -2 becomes y to the -1. Divide by -1 makes it into a minus. Add 1 to your exponent. Y to the -3/2 becomes y to the -1/2. Divide by -1/2. There's already -3 in front. What's your coefficient going to become? +6. So it's the same as multiplying by -2. That's -3 times -2. Okay. Y to the -3, add 1 to your exponent. Y to the -2. And now, what's your coefficient going to be? +3/2. So you're going to multiply by the flipped over version, right? -2 flipped over is -1/2. +7. Now, why do we treat 1 over y differently. Well, think of 1 over y as y to the minus 1. You're like, oh, just follow the rule. That's y to the 0, divide by 0. And then you're like, wait, what? Divide by 0? No, I don't want that. So that's why you have to do it differently. So what is the antiderivative of 1 over y? Natural log. And there we go, right? Is that our answer? Yeah, don't forget. Plus c. Plus c. All right, good. Any questions? Yes?
Can you explain the 3 halves again?
This one? So the rule here, and I didn't say this, are we bothered by the fact that it's y's and not x's? Well, maybe, but the procedure still works. So the procedure is if y to any power dy, you add 1 and divide by 1. Now, of course, not any power can't be negative 1. That's why you have to do the negative 1 separately. So here, you have your minus 3y to the minus 3. So minus 3 is a constant, and constants just come along for the ride. So negative 3. We add 1 to our power. Negative 3 plus 1 is negative 2. And then we're going to divide by negative 2. So negative, negative makes positive. 2 wrongs make a right. Well, no, not that. But 2 negatives make a positive. And then you have a 3 over 2. Anything else? All right. Cool. All right. Well, how much time do we have? We should still do another one. Let's do this one. So here, this is more closely like a word problem because there's words. And so we have to become comfortable with words. And so, earlier in our course, we talked about, if you have position, you can find velocity and acceleration. Now we're in the part of the course where it's like, we have acceleration. Now we can start to talk about velocity and position. So we say, okay, so the acceleration of a particle is given by this function, 2 minus 9 over 2 root t. Okay, well, we look at that and say, there's a better way to write that if we're doing calculus. What's a better way? What's a better way for us to write this function? Think calculus friendly. T to the negative 1/2. Because our rules are built around t to numbers. So if you see square roots, it's like, let's replace it by 1/2. If you see things downstairs, let's put it as upstairs, but with a negative power. Okay, so part A. Given that the object changes direction at time 4, find the velocity at time 1. Let's think about our understanding of acceleration and velocity. What's telling us direction? So direction is related to motion. Of course, all these terms, velocity and acceleration, are related to motion. How do we know direction? In particular, let me not try to say too much. What are we looking at if I want to know direction, which direction I'm traveling in? I see a hand way in the back. Yes?
It's positive or negative.
Okay, I like your answer, other than what is it? So you said if it's positive or negative, where it is
The number.
right. What number? You got a 50-50 chance. Acceleration or velocity? Yes! Yes! You nailed it! Okay, so velocity tells us about how things are moving. Now, velocity has two aspects to it. One aspect is the size of it. A larger number, you're moving faster. A smaller number, you're moving slower. The second aspect is the sign. So, if we see a positive number, we're moving to the right. A negative, we're moving to the left. If we want to change direction, what has to be true? So, we're not moving to the right, we're not moving to the left. What are we doing? We're kind of stopped. So, to change direction says we need the velocity at t equals 4 to be 0. So that's what that's telling us. Now, let's find our velocity function. How do you go from acceleration to velocity? Integrate. Okay, so what's the integral of 2?
2t.
2t. What's the integral? Minus 9 halves. Integral of t to the minus a half. T to the
1/2.
1/2, negative half plus 1, and then times 2. Right, dividing by half. Anything else? Plus c. Okay, now, can we figure out what c is? Do we have information? Is there anything available to us that might help us find c? Anything at all that might help us be able to determine c? Something that might give us a clue about what c is. Anything, anything. Oh yeah, we know something about what happens at time 4. We should use that. Okay, so 0 is the velocity at time 4. So we plug that in. 2 times 4 is 8. Here, by the way, the 2's cancel. Subtract 9. Square root of 4 is 2 plus c. 8 minus 18 is negative 10. Then we move it across. And we come to the conclusion c should be positive 10. Right? Because it's 8 minus 18, so it's a negative 10. We're trying to solve for c. So we now can say our velocity function is 2t minus 9 t to the 1/2 plus 10. All right. Now what's the part A asking us to do? Find the velocity at 1. So what do we do? Plug in 1. So the velocity at 1 is 2 minus 9 plus 10, because 1 to the half is 1. 12 minus 9 is 3, and we can even give them units. Our acceleration was centimeters per second squared, so our velocity is centimeters per second. Okay, so that's part A. Cool. Then there's part B. It says, given part A, find a second time the particle changes direction. So what do we need to do? Set the velocity equal to 0 and solve. And you're probably thinking, oh, is that even possible? Do we have the technology? 2t minus 9 t to the 1/2 plus 10 equals 0. Is that possible to solve? Now, on a side note, this is taken directly from an old exam. So it is possible.
Can we square both sides to get it to look more like a quadratic formula?
Oh. If you square both sides, you'll still have square roots involved. But I kind of like your thinking here. What's another way to think of t? X, okay, all right. What's another way to think of t?
X squared.
Well, we can think of t as t to the 1/2 squared. And you're probably like, what? How does that help us? Well, let's call t to the 1/2 a different name for a second. What do you want to call it? U? Sure. I was worried people were going to say, let's call it Jeremy. And they're like, no, that's too hard. But what do you have there? It's a quadratic. So if you have a quadratic, you can solve. But we actually have a cheat in that we kind of know how to solve it because we know one solution. What solution do we know? We know at time 4, things have to be 0. Well, if t is 4, what is u?
1.
U will be 2, because u is t to the 1/2. Well, that tells us that if u equals 2 is the solution, u minus 2 has to be a factor. That's the only way that's possible. So that gives us 1 out of 2 factors. So now you think of, well, u times what gives 2u squared? 2u. Minus 2 times what gives 10? Minus 5. I claim the other factor is 2u minus 5. Let's check. 2u squared, good news. Minus 5u minus 4u, nice. And a positive 10. Okay, so we already knew about the u equals 2. That leads us to t equals 4. What about 2u minus 5? When does that equal 0? Five halves. What time does that correspond to? Because remember, u is t to the 1/2. So t would be 25/4. Exactly what you probably thought when you looked at that. It's like, of course it's 25/4. What else could it possibly be? All right. Should we try for part C? Almost no space left. I like a good challenge. Any questions on part B? This was back in the day when they let me write problems. They don't let me write as many problems these days. I suspect this is one of mine. It feels like one of mine. All right, part C. Find the displacement of the particle between t equals 1 and t equals 4. Now, displacement, that sounds like a fancy word. What does displacement means? It's what? Volume? It can mean that in certain settings. Of course, there's the famous story of Archimedes running through the streets, yelling out, "Eureka! Eureka!" which was a displacement. And but in this case, it's not quite that, but it's a similar idea. It's how much has changed. So in that story, it's how much water was changed. So displacement of a particle is how much it's changed its location. So if I want to say the displacement between time 1 and time 4, that's saying look at where it's at time 4, subtract where it's at time 1. That's how much the particle has changed position. There's even a sign attached. It says, oh, I've moved to the left, or I moved to the right. So how can we find this? What would we need to do? Well, we need to find the position function, right? Because that's the position. We don't have that. We have acceleration, we have velocity. So what's the position function? What's s of t? So let's take the derivative of velocity. Antiderivative of 2t? T squared. Antiderivative of 9t to the 1/2. Well, the 9. T will be what power? 3/2 times that by 2/3. Antiderivative of 10? 10t. And then add a constant. Now we've already used c, so I'm going to start moving my way up through the alphabet. Not much we can do other than say, well, 9 times 2/3 is the same thing as 6. So t squared minus 6t to the 3/2 plus 10t plus d. And we don't have enough information to solve for d. Does that mean we can't answer the question? Because it kind of feels like, don't we need to know d to find the position at time 4? Well, we kind of do need to know d if we want to have the position at time 4, but I don't actually need the position at time 4. Because I'm after something else. I'm after a displacement. So let's plug in. So s of 4 subtract s of 1. Whoops. Okay. Let's try this again. Get the right number of parentheses. You know, you want your parentheses game to be on point. That's how you know you're going to do well in calculus. If you get all your parentheses, life is good. Okay, so plug in 4. 4 squared, and 7 years ago. Oh, wait, no, sorry, that's something else. 4 squared. 16. 4 to the power 3/2. Think of square root of 4, and then cube it. So 4 to the 3/2 is 8, and then times -6, -48. 10 times 4, 40. The d is the d. That's position at time 4. We don't know what d is, but hold on. Let's plug in 1. Now the good news is plugging in 1 is easy, because 1 to any power is 1. So you get 1 minus 6 plus 10 plus d. Well, what happens to your d's? They cancel out. So even though we don't explicitly know d, we don't need to know, because the displacement doesn't matter. And then we just have to play with the numbers. 16 plus 40 is 56. Subtract 48. That will give us 8 in the first. Subtract. 11 minus 6 is 5. 8 minus 5 is 3. What's our units? 3 what? 3 centimeters. And there we go. There's the answer for C. All right. Cool. And now in the last half of class, we'll actually do today's topic. Okay. The good news is we have plenty of time for today's topic. So, there's 2 sides of calculus. And we've been experiencing one side of calculus, which is differential calculus. How are things changing? Now, how do we do this? Well, we might say, how are things changing? If we see a function, then we say, well, the answer is kind of tricky because it depends. You say, okay, well, what if I change the question to instead of saying, how are things changing, I can ask, how is it changing right there? So what do? What's our philosophy? Derivative, which came from zoom in, and what happens? It looks a little bit less wiggly. But how do we make it even less wigglier? Zoom in. And so we said, if you zoom in, then lo and behold, things look flat. They look like lines. Lines, it's easy to talk about rates of change because that corresponds with slopes, and the idea of derivative is born. Okay, so that's differential calculus. We understand how things are changing by looking at these tangent lines and rates of change. So zoom in. Now we go to the second half, integral calculus. And we change the question. So before we say, well, how are things changing? Now it's, how much is the total? You might say, total what? Yes, the total. Most people think integral calculus is about finding total area. But it's more broad. It's just saying, I want to find the total of something. We start our intuition with area, but it does more than just area. So let's start with area. I have a curve, and it's doing something. And I say, I want to find the total area under the curve between 2 points. So A and B. That's the goal. How much total, in this case, area, but in general, again, how much total of something. So we start thinking, say, well, you know, when we were answering our first round of questions, differential calculus, we had a flat thing to help us. The line was our flat thing. Wouldn't it be nice if we had a flat thing here? And so we start thinking, well, what's a flat thing that we're really good with for finding area of? Rectangles, right? Rectangles, we're pros at finding areas of rectangles. How do you find the area of a rectangle? Length times width, yes? Base times height. No, whatever measurement on one side times the length of the other side, great. Life is good. Okay, so we're great with rectangles. But what's the problem? That's not a rectangle. What's the solution? We say, well, let's approximate it by rectangles. So what we can do is we can cut it up into little pieces, and then for each piece we'll say, I'll put a rectangle there and somehow shape form, and I'll approximate, and I can say, I can find the area of each of one of the rectangles, I add it up, and I get an estimate for the total area. And you say, yeah, but it's an estimate. It's going to be off. And you say, that's okay. It's not about getting it perfect right away, because I can do a better estimate. So how does one get a better estimate for the area? What do you need to do? Here, for differential calculus, we said zoom in. What does it mean to zoom in?
Smaller.
So, smaller in what sense? So smaller is the right kind of idea, but smaller in what sense?
Thinner rectangles.
Sorry, what?
Thinner rectangles.
Thinner rectangles, exactly. We're going to make really tiny, thin rectangles. And what's going to happen is these little tiny, thin rectangles are even better at approximating what's happening nearby. You might say, okay, but that's still an approximation. How do you get better? More rectangles, more rectangles. And they're going to get thinner and thinner. And it almost sounds like a limit, because it is. So that's what we're building up to. So that's the idea. That's where we're going. So we're going to answer the question to how much is the total by approximating it by a bunch of rectangles and then taking limits. That sounds like it's very time consuming. It is if you do it that way. But we're going to find a better way. But that will take us some time. So be patient with us. And I will say, computers love this idea of breaking things up into pieces and adding them up. You could say that computers, they love to compute. It's in their name. So of course they love it. All right. So we're going to introduce a topic. Riemann sums. Not to be pronounced Riemann. That's something else. That's an Iowa State thing. Riemann. So this was a mathematician, and he had the idea of like, let's just sort of get this process. We have these rectangles. Let's put them together. So here's the idea. We have our curve. And we're going to break it up. So we have our A and our B. And we're going to split up. A0 we'll call A. Then we have A1, A2, and so forth and so on. And let's just say in this case, 5. So we're breaking up into 5. And almost always we assume equal widths. Technically you don't have to, but we split it up into equal widths. Now, we're chopping up the interval from A to B. That's the downstairs. The upstairs, we have to say, that's one dimension. Now we need a height. So how do we pick a height? Well, for each interval, we pick a location. And you might say, but how? Okay, so there's a couple ways to do it. So for each part, so this is one of our parts here, use a function, and that really just says we're plugging in. So we have a point, we plug it in, that gets us the height of the rectangle to use. So that gives us our rectangle there. Now, what point do we use? The common points that we use, the left, the right, the middle, the midpoint. Less common, we can try to find the max value, the min value, but usually left, right, or midpoint is where we go. So, for instance, suppose I'm in my interval from A2 to A3. Which one is my left point? A2 would be on my left. Which one is my right point? A3. Where's the midpoint? Well, it's add them and divide by 2. That's the midpoint. So, the punchline here is the area is approximately, we have our, trying to think of how to write this in a convenient way. How is it written on here? Yeah, here we go. The value of the function in the first interval times the width of the first interval, plus the value of the function in the second interval, the width of the second interval, and so forth until you get to the value of the function in your last interval times the width of your last interval. So delta xi, this is your width, don't forget. F of xi, this is your height. So you're adding up a bunch of rectangles. So Riemann sums are rectangles. Add up a bunch of rectangles and you're approximating your area. Okay, so that's the philosophy. And we're going to spend a few lectures talking about this, so we'll get good at it. Any questions about the idea? Okay, so let's do some practice. Estimate the area under y equals 4x squared, where x goes from 0 to 4, using Riemann sums with 4 equal intervals, using left points, right points, midpoints. Okay, so let's start by talking about how we're breaking things up. We're going from 0 to 4. We want to break it up into 4 equal intervals. How do we know that? Because it tells us. So, given that they're equal in size, how big will the intervals be? What's the total length from 0 to 4? 4. If I want to split 4 up into 4 equal parts, what's the width of each part? 1. So that's actually very conveniently spaced. So there's 1, 2, 3, 4. So here, the widths are 1. So, for the left point, I come to the first interval. Which is my left point in the first interval? 0. So it'll be f of 0, that's my height, times my width, 1. For the second interval, what's the left? So 1, and then again times by the width. Third interval, it'll be 2, and for the fourth interval, it'll be 3. Well, we can plug these numbers in. What is f of 0 times 1? This is our f. 4 times 0 squared, 0. 4 times 1 squared will be 4. 4 times 2 squared, 16. 4 times 3 squared, 36. Add those together, 56. Okay, so that's an estimate. It's not the answer. Riemann sums are not about getting it exactly right. If they do, it's a coincidence, and that's okay. It's all about estimating. Okay, so now let's do the right points. You say, we should have always done the right points. They seem more correct. For the first interval, what's the right? It's 1. So the height will be f of 1, width will be 1. For the second, which is our point we pick? 2. F of 2 times 1. For the third interval, 3. So f of 3 times 1. Height, width. For the fourth interval, 4. Now some of these we've already computed. For example, we know that f of 1 is 4. F of 2 was 16, and f of 3 was 36. So I'll just copy the work we did. What is f of 4? 4 times 4 squared. 64. So this becomes 56 plus 64, also known as 120. So one estimate is 56. Another estimate is 120. You might notice these are not very close. What does that tell you? Probably not very good estimates. But that's not too surprising because there's a lot of real estate between 0 and 4. And we're only splitting up into 4 pieces. And you might say, well, why don't we split it up into 20 pieces? And then you realize, I don't want to add up 20 things. So you're like, let's keep it at 4. I'm all of a sudden, I'm on board with 4. Okay, for midpoints. What do we have? Well, what's the midpoint of the first interval? What's halfway between 0 and 1? A half. What's halfway between 1 and 2? 1.5, or 3 halves. So f of 3 halves times 1. Halfway between 2 and 3?
5 halves.
5 halves. Halfway between 3 and 4?
7 halves.
7 halves. So 1/2 squared times 4, also known as 1. Right, this is a quarter times 4. 3/2 squared times 4 becomes 9. 9/4 times 4. 5/2 squared times 4 becomes 25. 25 over 4 times 4. 7/2 squared times 4? 49. Now, 1 plus 49 is 50, plus 75. Sorry, plus 25 makes 75, plus 9 makes 84. And there we go. So that's the idea. That's the idea. So we have a minute left. I might as well, just for fun, I think I have somewhere in here. Oh yeah, here we go. What's an approximation for the area under the curve y equals 5x over 1 plus x squared from 1 to 4, doing a Riemann sum where we do a partition to 3 equal parts and we choose the left-hand points on each part of the partition. All right. Think about your widths. What are all our widths? Think about which points you plug in. Plug in those points. You put it all together. Survey says 6. All right. So Riemann sums, we'll get more practice next time. Have a good day.